How do large language models work? Explaining parameters, tokens, context windows, and embeddings. Aloha. Have you ever wondered how those incredibly smart AI chatbots work? The ones that can write stories, answer complex questions, or even help you code. These are often powered by something called large language models, or LLMs. LLM may seem like mysterious black boxes at first, but we can break them down into a few simple building blocks. When you scroll through AI headlines, you might see something like, "This new model is the world's most powerful AI, with 600 billion parameters, and the context length allows 200,000 tokens." That sounds impressive, but what does it actually mean? The first concept to understand is parameters, which you can think of as the model's brain cells. Just as the human brain contains billions of neurons that adjust their strength as we learn, an LLM contains billions, or even trillions, of parameters. These parameters are basically tiny knobs that tune themselves during training so the model can recognize patterns in language. When we say parameters are tiny knobs, we're really talking about numerical values, weights, inside the neural network. Each parameter is like a dial that influences how strongly one artificial neuron's signal passes to the next. During training, the model looks at enormous amounts of text and tries to predict the next token. Each time it guesses wrong, the training algorithm, backpropagation, makes tiny adjustments to millions or billions of these weights. Over time, those adjustments accumulate so the model gradually gets better at recognizing patterns. In short, LLM aims to pattern recognition. The more parameters a model has, the more complex patterns it can potentially capture, though it also needs much more data and computing power to train. Next are tokens, the building blocks of language for an LLM. A token is not exactly the same as a word. It might be a whole word, a part of a word, or even just punctuation. For example, the word unbelievable might be split into the tokens un, believe, and able. The model doesn't see words the way we do, it only sees sequences of tokens, which it then tries to predict one at a time. If you've ever played a word guessing game where you fill in the next letter or word, you're doing something very similar to what an LLM does when it generates text. The next crucial concept is the context window, which consists of tokens. The context window is like the model's short-term memory. Imagine having a conversation with a friend who can only remember the last few pages of what you said. That's how an LLM works. It can only hold a certain number of tokens at once, whether those tokens are from your prompt or from its own generated output. For example, if a model has a 4,000 token context window, that's roughly the length of 8 to 10 pages of text. Once that window fills up, the oldest tokens are pushed out of memory, meaning the model can forget earlier parts of the conversation. Here's where the 2004 movie 50 First Dates gives us a perfect metaphor. Set in Oahu, Hawaii, the story follows Lucy Whitmore, played by Drew Barrymore, who suffers a brain injury from a car accident that causes her memory to reset each night. Every morning she wakes up with no recollection of the day before. Henry Roth, portrayed by Adam Sandler, falls deeply in love with her, but each day he must reintroduce himself, remind her of who she is, and patiently rebuild their relationship from scratch. LLMs work much the same way. Once the context window fills up, older parts of the conversation are forgotten. Unless information is reintroduced, the model can't recall it, just like Lucy waking up with no memory of yesterday. Nonetheless, LLMs are getting better and better. For example, Google's Gemini models include versions with context windows up to 2 million tokens. In practical terms, this allows Gemini to process and reason over an enormous amount of information in a single request, such as entire books, hours of video and audio content, or massive codebases containing tens of thousands of lines of code. Some people have begun treating chatbots as AI companions, even going so far as to give them human names and interact with them as if they were friends or colleagues. But since a chatbot's context window, its short-term memory, can only hold a limited amount of conversation at once, these systems need another way to sustain longer relationships. That's where long-term memory comes in. Instead of cramming everything into the short context window, the AI stores key facts about the user, like their profession, interests, or past conversations, in a separate memory system. These facts don't live inside the model's billions of parameters, which are fixed after training, nor do they stay permanently in the rolling chat window. Instead, they're kept in a structured database outside the model and are selectively reinserted into the context window only when relevant. This way, the AI can remember important details across sessions, making the interaction feel more personal, consistent, and companion-like, even though its natural memory is limited. To make sense of tokens, the model uses embeddings, which are a way of turning words into numbers. You can think of embeddings as coordinates on a map, where similar words are placed closer together. For instance, cat and dog might end up near each other, while banana would be much farther away. This numerical representation allows the model to capture relationships and meanings, so when you ask about kings and queens, it understands that they are related in a way similar to man and woman. In other words, embeddings transform language into a kind of geometry, where meaning can be measured as distances and directions. So, how do all these concepts work together? When you give an LLM some text, it first breaks the text down into tokens. These tokens then enter the model's context window. Using its vast network of parameters, which represent all its learned knowledge, the LLM analyzes these tokens within the context window. It then predicts the most statistically probable next token to continue the sequence. This process repeats, token by token, until a complete and coherent response is generated. Together, parameters, tokens, context windows, and embeddings form the foundation of how LLMs work. The parameters provide the intelligence, the tokens are the language units, and the context window defines the scope of immediate understanding. Together, they enable the LLM to perform its impressive feats of language generation and comprehension. Put it another way, they are like the brain cells, Lego blocks, working memory, and maps that allow these models to read, write, and reason in ways that often feel surprisingly human. By understanding these basics, we can begin to appreciate both the power and the limitations of the technology that now shapes so much of our interaction with information. I hope this information is helpful to you. If so, please like, comment, share, and subscribe. If you are an instructor, please feel free to include this video into your lessons. Thank you for watching. Mahalo.